In 1977, NASA loaded 2 spacecraft, each the size of a Honda Civic, into a rocket and sent them off on a 5-year mission to explore our solar system's outer planets. The story of Voyager 1 and its twin, Voyager 2, begins in the late 1970s. A rare planetary alignment occurred, an event that happens only once every 175 years. The gas giants, Jupiter, Saturn, Uranus, and Neptune, lined up on one side of the solar system, creating a unique opportunity to study them in a single mission. NASA seized this chance, launching Voyager 2 on August 20th, 1977, and Voyager 1 on September 5th, 1977. Voyager 1, despite launching second, overtook Voyager 2 thanks to its faster trajectory, reaching speeds of 38,000 miles per hour compared to Voyager 2's 34,360 miles per hour. Just 13 days after launch, Voyager 1 captured a historic photo of Earth and the Moon from a distance of 7.2 million miles, a symbol of the start of their grand journey. On November 14, 2023, Voyager 1, the farthest human-made object from Earth, suddenly fell silent. For months, it sent back only a meaningless stream of binary data, leaving scientists to fear that the spacecraft, which had ventured beyond the solar system, was lost forever. The cause? A memory failure in its onboard flight data system, FDS, risking permanent loss of communication. But the team of scientists refused to give up. In a bold move, they decided to reallocate code to other areas of the probe's memory. This risky process began on April 18, 2024. Each attempt was a step into the unknown, as the signal took 22.5 hours to reach Voyager 1 and another 22.5 hours for a response. Just 2 days later, after months of intense work and nail-biting anticipation, something incredible happened. Voyager 1 re-established contact. What extraordinary discoveries did Voyager make at the boundary of the solar system? Why did this region turn out to be so different from what scientists had imagined? And what was contained in the mysterious signal that Voyager 1 sent after months of eerie silence? Jupiter, the first stop. In 1979, both probes reached Jupiter, revealing its previously unknown rings, discovering 3 new moons, and capturing detailed images of its largest satellites. They confirmed that Ganymede is the largest moon in the solar system, surpassing Titan, which was previously thought to hold that title. Voyager also discovered that Europa's surface is covered in smooth ice riddled with cracks, giving rise to the hypothesis of a subsurface ocean, a topic we've explored in another video. Additionally, scientists got their first close-up view of Jupiter's Great Red Spot, a centuries-old storm larger than Earth. Jupiter was just the first stage of their grandiose journey. Using its gravity for a speed boost, both probes set their sights on Saturn, the pale blue dot. Most of Voyager's discoveries taught us about the solar system beyond Earth, but they also hinted at what it means to be human. In some of the last photographs that Voyager 1 took before leaving our planetary environment, it turned its eye toward home one last time. While Voyager 2 explored Uranus and Neptune, Voyager 1 had another chance to make history. On February 14, 1990, from a distance of 3.72 billion miles, it captured Earth as a tiny pale blue dot, just 0.12 pixels in size. This iconic photo, known as the pale blue dot, became the last image ever taken by Voyager 1 before the cameras on both probes were permanently shut down Saturn. A turning point. The probes reached Saturn in 1980 and 1981, marking a turning point in the Voyager mission. Initially planned to last only 4 years to study Jupiter and Saturn, NASA had designed the trajectories to allow for potential exploration of other planets. A key decision was Voyager 1's close approach to Titan, the only moon in the solar system with a dense atmosphere. This decision ultimately directed Voyager 1 toward Titan, sacrificing its ability to continue the journey, while Voyager 2 was sent onward to Uranus and Neptune. The probes delivered detailed images of Saturn and its rings, revealing that they consist of hundreds of narrow, intricately structured rings. 4 new moons were also discovered, with Mimas being of particular interest. Its massive Herschel crater gave it a striking resemblance to the Death Star from Star Wars. Titan, however, harbored an unpleasant surprise. Its atmosphere was opaque to visible light, preventing scientists from uncovering the mysteries of its surface. Analysis showed that Titan's temperature was close to the triple point, a unique condition where methane behaves similarly to water on Earth. Uranus and Neptune, the ice giants. After Saturn, the paths of the 2 probes diverged forever. Saturn's gravity significantly accelerated Voyager 1, altering its trajectory and making it the fastest spacecraft in history. Voyager 2, meanwhile, continued its planetary tour, heading for Uranus next. Voyager 2 reached Uranus in January 1986, coming within 50,600 miles of its surface. Scientists were surprised to find that Uranus was vastly different from Jupiter and Saturn. While the gas giants are composed of 90% hydrogen and helium, Uranus contains these elements only in its atmosphere. Beneath lies an ocean of water, ammonia, methane, and hydrogen sulfide, with a core of rock and ice at the planet's center. Later, planets of this type were given the name ice giants. Uranus also turned out to be the coldest planet in the solar system, even colder than Neptune. After collecting data on Uranus, Voyager 2 moved on to its final target, Neptune. It reached Neptune in August 1989, becoming the only spacecraft to visit the 8th and most distant planet in the solar system. On August 25, 1989, Voyager 2 captured the first detailed images of Neptune, completing its grand tour. The planet appeared vividly blue, though later data revealed its true color is closer to teal. Into the unknown, interstellar space. Next, our cosmic travelers entered a long period of calm, lasting a decade and a half, which was interrupted by an extraordinary event. On August 25, 2012, Voyager 1's instruments recorded a sharp drop in charged particles emitted from the Sun, along with a rise in galactic cosmic rays. This meant that the spacecraft had finally entered interstellar space, leaving the region where the Sun's influence ends and interstellar radiation dominates. The slower-moving Voyager 2 crossed the same boundary in November 2018. The unique bubble of our solar system, called the heliosphere, extends about 11 billion miles from the Sun. It's formed by the solar wind, a stream of particles from the Sun, and ends at the Heliopause, the boundary between the heliosphere and the interstellar medium. The Voyager spacecraft have had smooth sailing through interstellar space, but Voyager now faces new risks far, far from home. This includes radiation, notes Jamie Rankin. She's a space physicist at Princeton University in New Jersey. Rankin joined the team as a graduate student in 2012. That was just days after Voyager 1 entered interstellar space. She's now working alongside Spilker as one of Voyager's project scientists. Cosmic rays are high-energy particles that whiz through space at nearly the speed of light, and they're much more abundant in interstellar space than in our solar neighborhood. On Earth, galactic cosmic rays are heavily shielded by the Sun, Rankin says. But there are a lot more of those out there where the Voyagers are. Some cosmic ray might hit a computer chip and fry it. Luckily, Rankin notes, the Voyager's age actually provides an advantage in dealing with these rays. Because their computer technology is so old, and therefore large, it can survive more hits than newer technology can. The Voyagers are the only spacecraft to have crossed this boundary and exited the solar system. What they discovered out there sparked widespread interest and active discourse among scientists. Shocking discoveries at the edge. Previously, it was believed that the solar wind gradually weakens as it gets further from the sun. However, data from the probe showed that the solar wind doesn't fade, but instead reaches a sharp boundary. Beyond this boundary, its influence ceases, and interstellar space begins. This means the solar wind doesn't simply dissipate, but changes direction, forming a physical boundary between the two environments. The solar wind flows around the heliopause from the inside, while interstellar plasma flows around it from the outside. We were also able to determine the shape of the heliosphere. On one side, it resembles a sphere, while on the other, it stretches into a long tail. Curiously, this shape is not static. The boundary of the solar system is constantly moving, distorted by massive waves that appear at unexpected, non-uniform angles. These waves can reach 10 astronomical units, equivalent to 10 times the distance between the Earth and the Sun, or about 930 million miles. Voyager phones home. Keeping the aging spacecraft running smoothly has required feats of engineering. This was the case in November 2023, when Voyager 1 stopped transmitting readable data back to Earth. Bob Rasmussen, a software engineer at NASA's Jet Propulsion Laboratory, is part of the team responsible for keeping the Voyager spacecraft up and running. Rasmussen worked on the Voyager mission when it first launched. He came out of retirement in 2022 to help keep the mission going. A broken memory chip onboard Voyager 1 caused a communications shutdown in 2023. The spacecraft could receive signals but no longer send any back. Despite the urgency of fixing Voyager's data transmission, the team took its time to work carefully. All hard problems need to be solved step by step, starting with what you know and building from there, Rasmussen says. Walking our way through this maze took a few months, but we finally figured out what had happened. It took sending different signals to Voyager to test which parts of the system were working. This task was made especially difficult because the decades-old papers explaining how these systems worked were written by hand or on typewriters. They couldn't be easily searched. Also, owing to the craft being 15 billion miles from home, each message took nearly a full Earth day to make a one-way trip. Thanks to the team's persistence and smart engineering, Voyager 1 started sending usable data again in April 2024. Thanks to the Voyagers, scientists also learned that the interstellar magnetic field is 2 to 3 times more powerful than previously thought. This, in turn, means that interstellar particles exert 10 times more pressure on the heliosphere than expected. The data obtained from this interaction provides a more comprehensive understanding of what occurs between the Sun and interstellar space. These insights can be applied to all stars studied by astronomers, as it's believed that other stellar systems likely share the same properties and processes as our solar system. The mysterious signal. Throughout their journey through interstellar space, the Voyagers have continued sending signals to Earth, transmitting data about the status of their instruments and their locations. However, in 2022, Voyager 1 unexpectedly transmitted a strange signal while 14.6 billion miles away from Earth. It began transmitting chaotic data about its position, sequences of zeros or the number 377. This mysterious signal puzzled scientists. The numerical sequence could have either contained critical information or indicated a malfunction. Later, it was discovered to be the latter. The issue was related to the spacecraft's altitude control and maneuvering system. Although it was still possible to control the spacecraft manually, Voyager 1 lost precise awareness of its position, likely due to cosmic radiation affecting its navigation system. NASA engineers successfully resolved the issue by transmitting telemetry through another onboard computer. Another alarming event occurred when Voyager 1 went silent for an extended period, starting on November 14, 2023, and lasting 5 months. This was caused by corrupted code on one of its chips. To fix the problem, the team made the bold decision to reallocate the code to other sections of the onboard computer's memory. On April 18, 2024, the process of transferring the data began, which required significant time. After sending the signal, the team had to wait 22.5 hours for it to reach the spacecraft and another 22.5 hours for a response. By April 20th, the team confirmed the success of the operation, and after 5 months, scientists were able to restore communication with Voyager 1 and verify its functionality. The final chapter. These malfunctions remind us that the lives of our cosmic travelers are nearing their end. NASA hopes the Voyager's instruments will function until 2025, after which a phased shutdown will begin. In a few years, the spacecraft will lose the energy needed to communicate with Earth, likely around the 50th anniversary of the mission. This will mark the final chapter of this project. Even after losing contact, these cosmic travelers' journeys will continue. They may witness many fascinating phenomena, though they'll no longer be able to tell us about it. Voyager 1 is moving away at a speed of about 3.5 astronomical units per year. 1 astronomical unit is the average distance between the Sun and Earth, approximately 93 million miles or 150 million kilometers. Voyager 1 is currently heading toward the constellation of Ophiuchus. In the year 4272-38,200 years from now, it will approach within 1.7 light-years of a little-known star in the constellation Ursa Minor called AC plus 79, 3888. Its twin, Voyager 2, is leaving the solar system at a speed of about 3.1 astronomical units per year. Around 40,000 years from now, it will approach within about 1.7 light-years of a star named Ross 248, a small star in the constellation Andromeda. Currently, Voyager 1 is approximately 15.5 billion miles away from Earth, while Voyager 2 is 12.4 billion miles away. Although they passed the Sun's Heliopause long ago, it's not entirely accurate to say the Voyagers have fully exited the solar system. Scientists believe the solar system encompasses everything within the Sun's gravitational influence. Today, it's hypothesized that the final frontier of this influence is the Oort cloud, a hypothetical spherical region surrounding the solar system that serves as the source of comets that periodically enter our planetary system. The Oort cloud includes 2 distinct regions, the spherical outer Oort cloud and an inner disc-shaped region. The estimated distance to the outer edge of the Oort cloud from the Sun ranges from 50,000 to 100,000 astronomical units, equivalent to the distance light travels in a year. Voyager 1 will take approximately 300 years to reach the inner edge of the Oort cloud and possibly around 30,000 years to traverse it, marking its ultimate departure from the solar system. The local bubble, a cosmic coincidence. Voyager 1 and Voyager 2 launched from Cape Canaveral less than a month apart. By the way, Voyager 2 launched earlier, but since it had a different flight path, it flew to the edge of our solar system second, 6 years after its colleague. Both devices found a very strange anomaly. As you move away from the Sun, the density of space increases. Interstellar space is usually considered a vacuum, but this is not entirely true. The density of matter is extremely low, but it still exists. In the solar system, the solar wind has an average density of protons and electrons of 3 to 10 particles per cubic centimeter, but it's lower the farther from the Sun. The smallest density of space is at the edge of the solar system. This boundary is called the Heliopause. At it, the speed of the solar wind, the flow of charged particles emitted by the Sun, or in other words solar plasma, drops to 0. The area between the Sun and the Heliopause is called the heliosphere. This is a kind of bubble in which all the planets of the solar system are immersed. At this boundary, the density of protons and electrons is 0.002 particles per cubic centimeter. According to calculations, The density of particles behind the heliopause, that is, in interstellar space, should be 0.037 particles per cubic centimeter. The Voyager 2 instrument showed that the density outside the solar system at a distance of 119.7 astronomical units, or 17.9 billion kilometers, from the Sun, was 0.0399 particles per cubic centimeter. This almost coincided with the calculations. But then the strangeness began. At a distance of 24.2 astronomical units, or 18.5 billion kilometers, the density was 0.12 particles per cubic centimeter. Why is the density increasing? We'll definitely talk about this a little later, but for now, let's talk about another bubble, much larger than the heliosphere, so that you'll appreciate all the thoughtfulness of the cosmos that packed us into two bubbles at once and understand the relationship between them. When you look at pictures of deep space, you get the impression that it's filled with clouds of interstellar dust and luminous gas. But back in the 1970s and 1980s, astronomers began to pay attention to the fact that the galactic space around the Sun differs from this picture. The solar system seemed to hang in an almost absolute void. This year, scientists at the Harvard-Smithsonian Center for Astrophysics, CFA, proved that yes, we really are in a kind of void. They conducted the most complex computer simulations, creating a three-dimensional reconstruction of space and time. The study showed that the Sun and Earth are located almost in the center of a giant bubble with a diameter of 1,000 light-years, which they called the local bubble. According to calculations, it began to form about 14 million years ago. For this, it's necessary that about 15 supernovae explode over several million years. This series of explosions pushed the interstellar gas outward with the pressure of light, creating a bubble-like structure with a dense surface at the boundary. And now, the bubble continues to grow in size. When the bubble first formed, it was expanding at about 60 miles per second. According to data collected by the European Space Agency's Gaia Space Observatory, at present, the bubble is still expanding at 4 miles per second. On its surface, 7 star formation regions were detected, dense molecular clouds where stars are formed. The process of star formation occurs everywhere on the surface of the local bubble, and there are many such bubbles in the galaxy. Therefore, it's possible that there are other stars, even with planets, which like us are also in their local bubbles. Interestingly, the Sun was not at the center of our universe at first. When these catastrophic explosions occurred, the Sun was far away from the scene, about 1,000 light-years away. But as Johann Alves, an astrophysicist at the University of Vienna, explained about 5 million years ago, as it orbited the center of the galaxy, the Sun got almost right at the center of the bubble. This is consistent with estimates of radioactive ion isotope deposits from a supernova in the Earth's crust from other studies. The researchers suggest that there are probably more star formation bubbles in the Milky Way. Research author and astronomer of CFA Alyssa Goodman, who founded GLUE, explains in her statement that statistically, the Sun would not be near the middle of a huge bubble. The Voyager missions have fundamentally changed our understanding of the solar system and interstellar space, from the discovery of active volcanoes on Io to the revelation of the heliosphere's complex interactions with interstellar space.